Welcome back to Forge College. So, in our last explainer, we laid out the foundational architectural blueprints for both the EVM and the SVM. We mapped out the executor, the runtime, the state store, the whole shebang. But, having the map is one thing. Actually driving on the roads, that's entirely another beast. Think of today's explainer as your absolute masterclass in chaotic traffic management. We're going to look at exactly how these two very different virtual machines process incoming transactions. We've got the static components, but now we really need to dig into the step-by-step execution details. Here is the engineering schematic for today's explainer. We'll start with Section 1, EVM, the single file line. Then we'll shift gears into Section 2, SVM, the parallel highway. Next up is Section 3, resource metering, gas versus compute. And finally, Section 4, tracing a real transaction.
Okay, let's dive right into this, because honestly, transitioning from that static architecture to the dynamic real-time flow of transactions, that is where the real magic happens. How do instructions actually get scheduled? How do we guarantee a predictable result every single time? And what happens when the system is just pushed to its absolute limits?
Section 1, EVM, the single file line, sequential ordering. Let's start with the Ethereum virtual machine. If the EVM were a piece of physical infrastructure, it would basically be the ultimate unyielding single-lane toll booth. Every single transaction has to wait its turn. There's no cutting in line, and there is absolutely no driving side by side. You check the gas, you run the instruction, and you revert if it fails. This strict one-at-a-time sequence is what makes the EVM highly predictable. Literally, every computer in the network replays those exact steps in the exact same order, so everyone ends up with the exact same result. It's just elegantly simple to validate.
But what happens if something goes wrong? Imagine you drive up to that single-lane toll booth, pay half your toll, and then suddenly you just run completely out of gas. In the real world, you're causing a massive horn-honking traffic jam. But in the EVM, they avoid that chaos through a snapshot and revert mechanism. It's honestly kind of funny to think about. It's as if you and your car are just magically teleported back to your driveway, the toll booth gets sudden amnesia and forgets you were ever there, and everything just resets. Though your wallet is definitely a little lighter from the gas you already burned.
Moving on to Section 2, SVM, the parallel highway, deterministic scheduling.
Now, if the EVM is that single-lane toll booth, the Solana virtual machine is a sprawling, multi-lane smart highway. It is purpose-built for massive throughput and parallel execution. It absolutely does not want transactions waiting in line if they don't have to. The SVM achieves this by acting like a ridiculously smart traffic cop. It uses a scheduler that lets multiple cars drive side by side at incredibly high speeds. Basically, as long as two transactions aren't trying to park in the exact same spot at the exact same time, the SVM is going to let them run concurrently in entirely different lanes.
So how does it prevent massive pileups at those speeds? Well, it uses something called an access set. Think of this as having to explicitly declare your destination before you even get on the highway. A transaction has to declare up front exactly which accounts it plans to read or write to. Determinism on the SVM relies entirely on the scheduler strictly enforcing these rules before you ever hit the fast lane.
And this brilliantly illustrates the fundamental difference between the two. The EVM relies on an implicit, strict single sequence per block to maintain order. The SVM, on the other hand, it requires an explicit, deterministic plan from its scheduler to safely manage that parallel execution.
All right, Section 3, resource metering, gas versus compute, accounting for the cost.
Let's see how this builds into the economics of the system, because whether you're on a single-lane road or a huge multi-lane highway, somebody's got to pay for the infrastructure, right? Resource metering dictates how we account for the cost of execution so the whole network doesn't just grind to a halt. Think of this engineering spec sheet as your guide to failure modes. In the EVM, metering is done via gas on a strict per-instruction basis. It's perfectly linear. If you run out, it reverts. Simple. But the SVM uses compute units to measure CPU and memory effort, and it utilizes a really smart pre-flight budget estimation. So a validator can actually look at an SVM transaction, kind of laugh, and say, yeah, you don't have the budget for this, and completely reject it before it even hits the fast lane and wastes parallel resources.
Let's bring it all together in Section 4, tracing a real transaction. Wallets A and B collide.
Because theory is great, but we really need to see this in action. Let's trace a real transaction to understand what actually happens when these execution models are pushed to their absolute limits under heavy contention. Imagine a scenario where two users, let's call them Wallet A and Wallet B, are interacting with the network at the exact same moment. This is the ultimate traffic bottleneck question.
What happens when two parallel lanes desperately need to merge because they want the exact same resource? If wallet A is trying to deduct tokens from account X and wallet B is trying to read the balance of account X to check a threshold, who gets priority? How does that conflict get resolved?
Well, in the EVM, it's honestly pretty straightforward. Whoever got in line first wins. The serialized block order strictly dictates the final state. If A is placed before B, B sees the new balance. Done. But in the SVM, because it's parallel by default, the smart scheduler spots that potential crash before it even happens. It'll briefly pause one transaction so the other can finish cleanly, making absolutely sure nobody ends up with corrupted data.
And if you peek under the hood at the pseudocode, the mechanical difference is crystal clear. The EVM is essentially just one giant loop. Run a step, check things, revert if you mess up. The SVM, however, is fundamentally a coordinator. Its job is to group the safe traffic together, run them all at once, and carefully commit the changes. The core architecture directly dictates the code.
Which brings us to our summary and next steps, tying execution to observable behavior.
So the crucial point is this. These aren't just philosophical design choices. As a developer, the way a VM executes transactions directly ties into the observable behavior of your smart contracts. It fundamentally changes how you write code, how you handle contention, and what kind of throughput your users will actually experience. To summarize our deep dive today, ordering defines observability, meaning if transactions can be reordered, their final states are going to reflect that order. Metering defines your failure modes. You either get a serial gas exhaustion revert in the EVM or a parallel pre-flight rejection in the SVM. Basically, the EVM gives you a canonical sequential trace, while the SVM gives you schedule-driven parallel execution. Simple as that.
These execution choices heavily determine which storage patterns are safe, which ones need explicit locks, and just how durable your data really is. And that is exactly what we'll be covering in our next explainer module, State and Storage Mechanics.
Before we go, I want to leave you with this slightly provocative thought. If execution limits truly dictate failure modes, how will your specific smart contract survive a sudden, massive traffic jam on the network? It's a question every single Web3 developer needs to answer. Thank you so much for joining me for this explainer by Forge College. To dive deeper into this subject and master even more essential Web3 topics, make sure to visit forge.college. See you in the next one.